Welcome to Logic First. In this video, let's learn the KMP algorithm. KMP is a string matching algorithm. We are given with a text string and also a pattern. We have to find the occurrence of this pattern in the text. First, let's have a look at the brute force or the naive approach to solve the string matching problem. It will then be easier for us to understand the KMP algorithm. With brute force, starting from the beginning, we consider every possible fit. We start with the 0th index. We have two different pointers for keeping track of the text and the pattern. If there is a mismatch in the beginning of the pattern itself, then we immediately move on to the next character present in the text. If the characters match, we increment both the pointers to check the next characters, and we continue doing this as long as the characters match. And when we find a mismatch later in the pattern like this, see here the index of the pattern is 3 and we find a mismatch here. We have actually started our comparison from the first index. Now since we have a mismatch, we move back I to the second index and start comparing from this position. We continue doing this until we reach the end of the text. Consider this worst case example of brute force. Whenever there is a mismatch, the text pointer is moved backwards and we are doing a lot of comparisons. Clearly, brute force is not doing well when we have more repeated characters like this in both the text and the pattern. Say the text is of length n and the pattern is of length m. In the worst case scenario, what we do is we first start with here and do m comparisons, and then we start here and do another m comparisons. So we keep doing this until this point, because there is no point in starting from this position. The pattern will anyways be truncated. So this is the final starting point, which is n minus m plus 1. So for each of these n minus m plus 1 characters, we are doing m comparisons. So the worst case complexity is this. Analysis of time complexity itself comes into picture only for very large inputs, right? So n is obviously going to be very large when compared to m, the length of the pattern. So this can be considered as O of n into m. We can ignore the m square and the m terms since they are going to be very small. Before directly jumping into the algorithm, let's first think how to improve the brute force technique. Consider this easy example. We find that the first 4 characters match and the last character is a mismatch. With brute force, we go backwards and start comparing from this position. This going back is what is making the brute force approach very slow, right? So how can we avoid going backwards? When we find a mismatch like this, we know that the previous characters match, right? In this example, the previous 4 characters of the pattern matches with the previous 4 characters of the text. We know that this and this match, this and this match. Then what's the point in going all the way back and trying to compare this with this? So instead of going backwards like this, once we find a mismatch, can we just start comparing the pattern from this position, from where the mismatch was found, ignoring altogether all the previous characters of the text? Let's see, it seems to work in this example. Here is a mismatch, so we move forward and we are able to match the entire string here. But this definitely is not the right approach. It is working in this example because all the characters in the pattern are distinct. Consider this example now. The first 5 characters match and there is a mismatch here in the last character. If we go by our previous technique, that is, if we just ignore all the previously matched characters and just start comparing from this mismatched position, just like this, we will not be able to find the required pattern which is actually present here. We will be missing it. By totally ignoring the previously matched characters, we will be missing the overlapping characters like O and N in this case. So how exactly do we find these overlapping characters? We know that the previous 5 characters of the text as well as the pattern match when there is a mismatch in the 6th character of the pattern, right? With this information, just consider this particular substring, the first 5 characters. We know that the exact same 5 characters are present previously in the text, right? So in this substring, we have to find a prefix that is also a suffix so that we can match this prefix of the pattern with the suffix of the text, and we can skip all the previous comparisons and start comparing from this third position or exactly the second index of the array. Moreover, it is not just some prefix that is also a suffix. It should be a longest prefix that is also a suffix. Only then we can correctly match them and skip maximum comparisons. Here we have the mismatch in the 5th index of the pattern, right? Which means the index 0 to 4 exactly matches with the previous characters of the text. So now consider only this substring. In this substring, the longest prefix that is also a suffix is of length 2. If we pre-calculate this information for each index of the pattern and store it in an array, that is, until that particular index, what is the length of the longest prefix that is also a suffix? If we have that information readily, we can easily look up this table and determine what is the next position that we have to compare whenever a mismatch occurs. In this example, the mismatch occurs in the 5th index, which means until the 4th index, all the characters have matched. And if I go to the 4th index of the table and if it tells me what is the length of the longest prefix that is also a suffix until 4th index, that is in this case, if it says 2, if I have that information, I will understand that the characters in the 0th and the 1st index are already matching. So it's enough if I start comparing from the 2nd index. I can skip all these comparisons without moving this pointer for the text. We are able to now determine from which position in the pattern we should begin our comparison. So this is what is the logic behind the KMP algorithm. You are just pre-calculating a table which tells you for each index what is the longest prefix that is also a suffix until that point. So when you are searching through the string, whenever a mismatch occurs, you just can look up that table and determine from where you should start comparing in the pattern without even moving the text pointer. This algorithm was developed by Newt, Morris and Pratt independently, and it is the first ever linear time algorithm for string matching. Unlike brute force, it totally avoids the re-examination of the previously matched characters. For this example, let's try to fill up the entire LPS array. LPS stands for the longest prefix that is also a suffix. When you are calculating for the 0th index, just forget about the remaining part of the array. The length of the longest prefix that is also a suffix for this particular character will be 0, right? While calculating for the 1st index, you have to take the first 2 characters into consideration. Here, again, the length of the longest prefix that's also a suffix is 0. O is the prefix and N is the suffix. They are not equal. So that's why we have a 0. If you take ONI, again it will be 0. If you have trouble in understanding this, just write down all possible prefixes and the suffixes for this substring. For ONI, O is a prefix. ON is also a prefix. Similarly, I is a suffix. NI is also a suffix. None of these match. There is no prefix that is also a suffix. So that is why we have a 0 here. Don't take ONI as a prefix and ONI also as a suffix. This cannot be done. Why I cannot consider ONI as a prefix as well as a suffix? See here, ONI, ON is a substring. I can very well consider that as a prefix as well as a suffix. But then I have to start comparing from this position. I already know that this position does not match. The logic of computing this LPS array itself will be meaningless if I take the entire substring as prefix. So that's why we are not doing that. We also commonly say the longest proper prefix that is also a suffix. By proper, we mean this only, that is, we cannot consider the entire substring as a prefix. Anything less than that is only a proper prefix. Now when we consider the first 4 characters, O is a prefix and it is also a suffix. That is the longest prefix that we can find. That is also a suffix. So here we compute 1. Taking the first 5 characters, ON is a prefix and it is also a suffix. The longest possible prefix and suffix. So we have 2 here. Now considering the entire pattern, again there is no prefix that is also a suffix. I have just written down all possible prefixes and the suffixes. Nothing matches. So here again we have 0. Let's see the implementation with Python. For the search function, we receive the pattern and the text as the parameters. First we compute the length of the text and store it in N, and then the length of the pattern is stored in M. We need to compute this LPS array. It should be of same length as the pattern. So we are initializing it with M zeros. We make use of a separate function to calculate the LPS. Let's get to the implementation of this function later in the video. First, let's finish off this search part. So during search, we have to compare starting from the beginning index of both the text and the pattern, right? So we need to have 2 different pointers for the pattern and the text. So we have I and J. and we are initializing them as 0 since we have to start from the beginning, we need to scan through the entire text input to find the pattern. So the loop runs until n, the length of the text. First we compare these two characters, and if we find a match, what are we supposed to do? We just have to increment both the pointers, right? So let's have that in an if. If the character at the text and the pattern matches, then we just have to increment both the pointers. The next 4 characters also match, so we keep incrementing the pointers, and there is a mismatch in the 5th index. When there is a mismatch in the 5th index of the pattern, we know that the index from 0 until 4 is a perfect match. So if we go to the LPS table and check what is the value at the 4th index of the table, it will tell us the length of the longest prefix that is also a suffix until this point, until the 4th index. It says 2. 2 indicates the length of ON. ON is the prefix and it is also a suffix. So when we see a 2 here, we can understand that the characters at the 0th and the 1st index are already matching with the previous characters of the text. So we can directly start comparing from the 2nd index like this. See, here the value of j is 5, and we now have to go to the 4th index and see what is the value in the LPS table. So that is why we are assigning LPS of j minus 1 as the new j, because this is where we have to start our next comparison. Notice that I is going to remain the same. Wherever the mismatch occurred, we are still in the same position, and we just have shifted j by looking up the LPS table. Since we are finding LPS of j minus 1, we cannot do that when j is equal to 0, right? If j is 0, that is, if the first character itself does not match, we cannot find LPS of minus 1. So we can do this only when j is not equal to 0. What are we supposed to do when the mismatch occurs when j equal to 0? Take this simple example. Here the mismatch occurs in the first character itself. J is 0. So we just have to go to the next character in the text, right? We just have to increment I and j remains the same. So that is what we are doing here. Again, coming back to this example, if all the characters have matched, j will be equal to m, the length of the pattern. We have progressed until the end of the pattern. So if that is the case, we now have to print what is the occurrence. 3 is the starting index, right? We only know I is 8 and j is 5. So we just have to print what is I minus j. If you want to continue searching for all the occurrences of the pattern in the text, we just have to reset j again to LPS of j minus 1, just like how we did here. We simply cannot search from this point. There might be some overlap here as well. That's why we reset j to LPS of j minus 1 and continue searching further till the end of the text input. Coming to the implementation of the LPS array, it is almost going to be same as what we did in the search function. In the search function, we had a text and a pattern. We used 2 different pointers to match the string. But for the LPS computation, we only have the pattern here. We are going to make use of 2 different pointers, but the string matching has to be done within the pattern itself. We are going to make use of this I to progress till the end of the pattern, and this length is going to actually tell us the length of the matching prefix that is also a suffix. To begin with, we can initialize length as 0 and I as 1. LPS of 0 will always be 0, because if you consider only the first character O, there is no prefix or suffix there. Here the length of the pattern is 6. I is going to move till the end of the pattern. So while I is less than m, first we compare these 2 positions. So when you are computing the LPS of I, just forget about anything that is beyond I. Just by looking at this string, we can see that we should get a 0 here because there is no prefix that is also a suffix and there is a mismatch during the comparison, right? So when we have a mismatch, let's write the else part first. In this case, we have to assign LPS of I as 0 and we only have to increment I here. Without finding a match, we cannot increment length, right? We are finding the length of the prefix. So it should start from here. Only if there is a O, then we can increment length. So we just increment I in this step and now again compare these 2 characters. Again there is a mismatch. We already have a code for mismatch. This will get executed and we will have a 0, which is correct. Now we can again increment I to compare these 2 characters now. We have a match here. LPS should now be assigned as 1, right? The length pointer is still at 0. But now the 0th index is a match. So we are adding 1 to that and then assigning to LPS of I, because array index will always be 1 behind in the count, right? So that is why we are adding 1 and then assigning it to LPS of I. Now since there is a match, we have to increment both the pointers. So we just increment the length and I. These two characters match, so this code will be executed, and we will assign length plus 1 to LPS of I. Length is now 1, so 1 plus 1 is 2, and it is correct because the length of the longest prefix that's also a suffix is actually 2. And again we increment both the pointers. Now there is a mismatch, so we just put a 0 here and increment I, and we reach the end of the string. So that's it, we have computed the LPS and it seems to be correct, but the else part here needs some changes. We will see why with a different example. Here in this example, we first put a 0 in the 0th index of the LPS, and we now compare these two positions. They match. So when they match, what we have to do? Just assign length plus 1 as the LPS of I. So here we put 1 and increment both the pointers. Now when we compare these two, there is a mismatch. So when there is a mismatch, according to our code, just put a 0 there and increment I. Just think, can I compare this and this now? Does it make sense? Already there was a mismatch here, which means we have lost the continuity. Say for instance we go by this code and compare these two positions. We have a match, and as per this code, length plus 1 will be 2, and we cannot put a 2 here. It is wrong. In this substring, there is no prefix that is also a suffix of length 2. We only have a and a here. So the length of the prefix that is also a suffix is of length 1 only. So whenever a mismatch like this occurs, and if we have already progressed in length, we have to go backward in direction, right? Otherwise we will lose the continuity. If we are still in the first position of the pattern, the length is in the first position of the pattern, then we can go by this code. It will work. That is why it worked for our previous example. But if we have progressed in length, we cannot go by this code. So when this length pointer is not equal to 0, we now have to think what is the new position for this length pointer. We would intuitively think to go all the way back and start from the beginning. That is, assign length as 0 and then continue our search. But again, this will not be correct. Let's see why. Let's just continue with this code. On comparing these two, there is a match, so this code will be executed. Length is now 0, so when we add 1, we get a 1 here, and it is correct. We increment both the pointers. On comparing these two, again they match. Length plus 1 is 2 now. And it is correct because now the length of the prefix that is also a suffix is of length 2, and our code is working properly. Now when we increment both the pointers and compare these positions, there is a mismatch. Since length is not equal to 0, according to this code, we set length as 0 and again compare these two positions. Based on this code, we will put a 1 here, but that is not correct. Just observe this substring carefully. The length of the longest prefix that is also a suffix is of length 2, right? A. So actually we need a 2 here and not 1. What is the problem here? Let me bring this part down so that now you can see this is going to be exactly the same scenario that we discussed for the search method. When there is a mismatch here, we know that this and this match. Actually, this is present here. Just because there is a mismatch here, we cannot start all the way from the beginning, right? But that is what we are doing here by assigning length as 0. This A has to overlap with this A, and we have to actually compare this I with the first position. But how do we know how many characters overlap? We have already computed the LPS until this point, right? So we just have to assign LPS of length minus 1 as the new length and then continue. Just like how we did for the search method. LPS of length minus 1 is now 1. So we just have to reset length to this position and then compare. They match. So as per this code, we can put a 2 here and increment both the pointers. And now there is a mismatch and length is not equal to 0. We again have to check if there is an overlap. So we assign LPS of length minus 1 as the new length and compare at this position now. Again there is a mismatch, so we go to this position 0 and compare. There is a mismatch, so we can put a 0 now. Since length is equal to 0, we execute this part of the code. We have both the method that we discussed, LPS and the search method. If you see here, it is the same logic. Here in the LPS computation, it is just a single array, but here we have two arrays. That is the only difference. Since this is one single array, it might seem little confusing, but if you compare these two, then you can easily understand the logic. Moving on to the time complexity, we know that the text pointer that we used in the KMP search method never move backwards, which means for each and every character present in the text input, we only perform some constant number of operations, including the LPS lookup. Since the number of operations is going to be a constant multiple of n, it can be considered as a O of n time complexity, that is linear time. During the computation of the LPS array as well, the pointer I never moves backwards. But here in this step, the length pointer actually moves backwards a certain number of times, and we have some extra table lookups. But this cannot occur for all the characters in the string. It can only occur after a certain number of matches. Assuming that this step occurs only a few times, this LPS array computation can be considered as O of m time complexity, linear time. But strictly speaking, it is not linear. It will be very difficult to accurately predict the time complexity of LPS array, but it is not necessary as well. Just think of the bigger picture here. This pattern array itself is very small when compared to the actual text input, right? So we don't have to waste our time in accurately predicting the time complexity of this array. So the overall complexity is O of n plus m, which can again be considered as a linear time. It uses O of m extra space for the LPS array. This algorithm is best applied when there are a lot of repeated characters in both the text and the pattern, like in DNA pattern matching. In DNAs, only the characters A, C, G and T are repeated again and again, but in normal text documents wherein you have to perform a search, brute force itself does pretty well. Thank you for listening.